71 batch. Warm welcome to you, sir.
Good
You
afternoon,
are
sir.
based out of Hosur and Bangalore, is it?
Yes, sir. I stay in Bangalore, work in Hosur.
Oh, I see. There will be a long commute every day, right?
50 kilometers.
How much? 60? Wow.
50,
And in
50.
50. And in Bangalore traffic.
Yes,
If
sir.
it is Chennai, it's okay, right? 50 kilometers, you'll do it in 50 minutes or even less than that.
I think
You work in Sri City in Chennai, then you can commute to Sri City from here, aram se.
Okay.
But I won't say the same thing about Bangalore. Highly unpredictable.
we have crossed 100. I think we can get started.
Krishna Kumar sir is there. Is Arun
is on
Dev
board.
there, Robin?
Yes, Arun Dev is there.
Okay.
I'm there, Ravi. I'm there.
Okay, we'll start.
Yeah.
So we have quite a number of champions. Krishna Kumar has joined also. Okay.
Ram sir, I am starting now.
Okay.
If
Good afternoon, one and all. Welcome to Theory to Practice lecture. Before getting into the session, so we need to follow some guidelines and the rules. So in this Zoom code of conduct, so all are stay muted. Please record your attendance in the attendance form, which will be posted in the chat box. If you have not already registered, please register the registration form, then you submit your attendance form. During the Q&A session, you can ask your questions or raise your hand option. Now, I request Mr. Ram to give the intro about PALS as well as the speaker's introduction. Ram sir.
Good afternoon to my young friends and to the professors who have joined the session, to the speakers of the day, and my colleagues in PALS. This is the second theory to practice lecture for this year. And then it's on a topic which is very important and is of interest to everybody. Ever since the wheel was invented, then the internal combustion engine is the most powerful prime mover which helped in transport. So today we have with us two eminent speakers on the topic engine testing, practical approach on diesel engine combustion development. And today you are going to have Dr. Ramesh Babu from IIT Madras. He's a veteran of over 20 years or more than that. He received his PhD from IIT Madras in 1990. You talk manufacturing, then you will have to talk about Dr. Ramesh Babu. And his research includes a vast field, Research is usually more and more of less and less. But a professor does more and more of more and more. So that's his experience. So it's a manufacturing technology, grinding, abrasive water jet machining, sheet metal fabrication, laser beam machining, CNC, PLCs and robotics, precision machine tool development, process modeling and simulation. So right from the basics up to the modern manufacturing tools are his areas of interest. And he has published 61 international journal papers and 104 national international conference papers. So today, Dr. Ramesh Babu will be laying the foundation, the theory of internal combustion engines. And then we have the second speaker from industry. It's a Yogesh Bolar, who received his MTech from IIT Madras in the year 2004. He is general manager in Ashok Leyland, engine testing and development. And then he has been through it all. It is right from component design, design verification, design validation, and combustion optimization, development of heavy duty diesel engine for heavy duty trucks, buses, defense and automotive application. So at this juncture, I would just, as a industry person, I would like to say that if you are doing something, you are in charge of development in core engineering, you have to know that all your products, whether it's trucks or whatever, anything, they should be designed for misuse, rather than being designed for use. So that has been my experience, and still they should last. And having been a sub-supplier to, in brake parts to Ashok Leyland, I know how they look at it. So you have the users who won't, be aware of all the sizes, but still the vehicles have to last. So, and I request all of you to make use of the opportunity. I hope you are all fresh this afternoon after your classes. Be very attentive, because we are bringing to the table people who are really both in theory and practice. We have resources who bring together all more than 50 years of experience. So with that, I hand over first to Professor Ramesh Babu, and then he will finish his presentation and hand over to Yogesh. And at the end of it, you'll have interactions. Thank you. Thank you for the opportunity.
Thank you, Mr. Ram. Can you hear me?
Yes, I can.
Okay, thank you, Mr. Ram, and a warm welcome to all the students and faculty members and other attendees to this particular session being organized by the PALS. I am Professor Ramesh Babu from IIT Madras, and my expertise is mostly on the manufacturing, advanced manufacturing. However, I have done a PALS event a couple of years ago along with the industrial partner. That's where I just came into the picture to really bring the theory which we covered at the institutions and colleges, and then practice that comes from the industry. Both are going to really make a mark in your minds to take up your career in course of time. Though I'm not an expert in the IC engines, but then I also have studied the IC engines. I was also heading the department wherein I have seen people working on the IC engines, especially the gasoline as well as the diesel engines in a very, very aggressive way over the last few years. So in that context, I have prepared a short presentation in order to tell you that what we do at institutions and colleges, and what happens in the industry in terms of developing the technologies and taking it to the last mile of giving it to the customers. I think all of you are engineering graduates, I suppose, and then you would have gone through some of these courses on the IC engines and thermodynamics, combustion. I'm not going to bore you with the material, but I'm going to give you some trends and the factors that motivate anybody to get into this area and then keep working in this auto sector for a few more decades, in view of several developments that are simultaneously happening now in the industry. So though you might think that industry is moving towards the electric vehicles, but it is a long way to implement them in certain vehicles which we see on road, like transport vehicles like buses and heavy trucks, and even the many transportation and cargo vehicles. So in that context, I have just made this presentation to tell you that what we are going to deal in this particular session is going to be on the IC engines, and I will let me share the my screen and then tell you about the hope you can see my screen clearly. Yeah.
Yes, sir.
Yeah, I think the reason why we wanted to be together to make this presentation is basically to bring the theory to practice, to give you some sort of a pathways and directions for you to choose the areas and also contribute in these areas. So the first and foremost thing is I just wanted to tell you all of you have gone through these courses right from your second year, and we used to start with heat engines where we have external combustion engines and also internal combustion engines. And I'm not getting into the external combustion engines, that is not our main interest in this particular session. So when we go into the internal combustion engines, so we have seen different types of systems. Depending on the way these systems are built, either a rotary motion or a reciprocating motion of the piston in a cylinder to create this combustion, and then provide the energy and work to the systems which are being driven as the vehicles. So from that angle, I just made this particular slide to give you a focus onto the diesel engines. And why are we still talking about the diesel engines, though they have been invented quite some time ago? But then you see the advancements in each and every area that I have highlighted here is the design of diesel engine is continuously evolving and becoming more and more better in terms of the emissions. And that's where most of you who are aware of the vehicles being produced by most of the industries, they keep talking about the Euro norms and Bharat stage norms, etc. I think Mr. Yogesh is going to touch upon all of them in his presentation. But I wanted to tell you that the most important things which we address while designing the engine is it should be lightweight. As the weight becomes more and more, the amount of power required to pull the vehicle also will increase. And that's where the economy of fuel usage will come into picture. And of course, once you do the combustion in this internal combustion engine and the emissions, there are certain particulate matter and gases, and all these things will be emitted. And these emission standards are becoming more and more stringent with the norms being followed for the green house effect and all the standards being evolved with the international community. So what we actually do in case of engine design is basically we look at the power of the vehicle in terms of the horsepower. Power that again depends on the amount of weight or amount of load to be carried by the vehicles. And we also bring out the torque characteristics of this engine also in order to ensure this acceleration, deceleration, and also braking, etc. So hence both on the road and off the road also these issues are extremely important. So hence the engineer who is dealing with the engine design deals with all of them. And I just wanted to show you that there are several components. I'm showing you only certain components related to the compression ignition engine, which most of you are familiar with. And if you start from the bottom, we know that crankcase where the cranking is done, and then the piston and the cylinder interaction. The piston interacts with some elements in the cylinder, and you can see at the top we have an injector, and that's where the fuel is injected into it after the compression of the air. And you will also find some of the valves for the entry of air into the chamber. That chamber is basically known as the combustion chamber, and you can see the piston and the crankshaft is connected through a connecting rod. So I think this is how we actually teach in the classrooms. And of course, you can also see several engines being connected with balancing and without balancing. And then you have a multi-stage, cylinders and multi-stage engine, blocks, etc. So one of the important thing is the combustion that takes place within the chamber. That is known as the combustion chamber. I think we also study this combustion phenomena since the combustion is not linear. It's highly unsteady and non-linear. So there are several simulation packages available now to study this sort of a combustion. And this combustion is essentially studied to see that the fuel is properly placed so that we get the maximum benefit from the fuel which is injected into it. I think while studying this combustion, we also look at the efficient way of using the fuel on one side, and also cleaning up of all these materials that are generated as the combustion byproducts, like NOx, hydrocarbons, and particulate matter, etc. So we use the catalytic reducers, and also using some sort of a recirculation systems. We also bring this exhaust gases, etc. So in all these cases, in most of the colleges as well as the institutions, and especially in the higher semesters, the electives are also offered to make them experience with the simulation. And most of you who are studying the final year, understand that the computational fluid dynamics plays an important role in the case of simulating the combustion and the combustion chamber. So apart from this one, what we actually look at the designing of an engine is basically to look at the fuel injection equipment, and nowadays we are using the electronic injection with computer controls, and that also takes care of some of the strategies in order to reduce the emissions by way of optimizing, some parameters. And while the piston is moving in the cylinder, and during the combustion, there is a certain amount of a noise. A noise can be due to the mechanical movement of various elements which are connected together, or due to the thermal gradients that are produced in the combustion chamber. So hence we need to reduce this noise, vibration and harshness. That's why many advancements have taken place in that area also. So while we go through the presentation by Mr. Yogesh, I think he's going to address all of them with a clear examples and the equipment and instrumentation. I think there are several phases while developing the engines, and I'm not getting into the details of ab initio design. Ab initio design is based on the requirements, and we want to come up with a new engine design. But most of the designs being modified by many the auto industries and automobile giants are basically looking at the modeling and simulation, and then making certain changes to the components and the associated elements with the entire engine system, etc. So here I just wanted to touch upon a few things, though the engine testing happens only at the end, but there are several phases which the students have to learn very systematically if they want to really follow why the testing and certification becomes most important and crucial in developing a new engines. And that's where the various prototyping techniques, when somebody is modifying the design, either by changing the combustion process or a combustion chamber, and this has to be tested, and proved that the prototype, which is developed based on the modifications brought about by means of a modeling and simulation, has to be experienced. I think I'll give one or two examples when we at IIT Madras was engaged in developing some new engine development with one of the auto industries. What we found was we normally tend to think that the cylinder is a real cross section is circular. But then when we did this analysis of a combustion and the heat generated in the combustion chamber, so we found that the entire combustion chamber is not exactly cylinder, even though we call it as a cylinder, but it keeps changing from cross section to cross section in order to handle the thermal load. And that thermal load comes due to the combustion, and also the amount of fuel being injected by the injection system, and then the compressed air is at the bottom, and all these things have to be taken into consideration while designing this entire the engine. So this is where the prototyping and then also experiencing comes into picture. In the current scenario of manufacturing, the prototyping can also be done by means of additive manufacturing with metallic processes. We call it as the additive manufacturing through various metals, etc. And then they use these technologies extensively to prove that the design is robust enough to take care in the continuous production. And then we need to give the tolerances and also find the suitable processes to create that sort of a shape in the entire cylinder also. So unless you do all of them, it is not possible for us to use these engines for the final production, which is going to be on large scale. So which we call it as a mass production. So hence in all these concepts, though you study at your undergraduate and postgraduate studies, but then the in-depth analysis of all these aspects is not covered by anybody in the academic institutions due to lack of experience, and then the textbooks are also not written in a way that the testing is actually done in the industry. So that is where you can really experience how this testing activities which are carried out in the real industry like Ashok Leyland. So you can experience them. And as you know that at the end of the session that Mr. Yogesh also planned for a quiz. So I suggest that you should be quite attentive and also be participative at the end. If you have any specific queries or specific doubts, you can also note down in your notebook and then come up with those queries, either in the chat box or maybe you can also unmute and then ask us some questions. So I think this is just to set the tone for the lecture, which is going to be made by Mr. Yogesh. So I just wanted to tell you that this is how we do the theory in the classes. And I think this can be translated into a practice, with several instruments and several test tricks and test protocols. And even the optimization of all these things can be done only after testing and verification. So I think with this a few set of slides and introduction, now I will come out of the sharing because Mr. Yogesh has a presentation which he can really share it and then give his experiences in this particular area. So I'm just Mr. Yogesh, I think I'm stopping it here. Okay.
Okay. Thank you, Professor, and thanks for this good introduction. Once for out, I'll be.
Yes. Yeah.
Thanks for this introduction, Professor, and you set a good lay down for the students to now go to the main topic. Let me share my presentation and then we'll. Sujata, I'm not allowed to share.
No, you can, sir.
Okay.
Are you having an issue?
Yeah, I'm not able to get into the share. Should I go to the advanced sharing option or multiple sharing?
No, just click on the share screen. That's it.
No, but it is going and asking one participant can share or multiple or advanced sharing.
So don't click on the arrow, just click on the share button, because if you click on the arrow, it will.
Okay.
Yes. Coming.
Okay.
Yeah.
You're able to see the screen.
Yes. Thank you, Professor, and I will be taking the session now. Good afternoon to all, and straight away going to the contents of my presentation, we will be seeing the overview of the engine testing, where I will be covering many topics. The hardware selection here, the assumption is we have a base engine which is on the vehicle, and then you are looking at upgrading that kind of an engine. So we'll be looking at what kind of a hardware that will be changing to meet the vehicle requirement. We'll go extensively on a topic which most of the students would be seeing a small inside your lab, which is usually a single cylinder or a multi-cylinder engine. But in an industry, it is a big setup for testing of engines for many of the durability, emission, and the performance and optimization. So the third topic would be the test cells or the test beds, what we call. Fourth would be the test cycles. What I mean by test cycles is you might have heard that the engine is meeting certain Euro 4 or Euro 6 emission norms, but these are all done under standard test cycle conditions, and then you have to meet this legislative requirements. So that will be covering some of the test cycles. Once they're in the test bed, you are there, you are collecting a lot of information in terms of pressure, temperature, peak firing pressure, so many data are coming. So how do you analyze this data is also being touched upon. This will be quite interesting that in the lab you would have seen a full throttle performance. I'll be covering a little more in the depth at how we analyze the data. And also I'll look at, because most of the modern engines are today electronic, we'll also be covering how an engine is optimized. How do you get the required power? How do you get the required the performance in terms of speed, in terms of response from an engine? Those things will be covered. And last, will be interesting that we will be open the question and answers. Let us see what questions come up. So overview of the engine testing. So basically, you can see there are different boxes here, which is telling how an industry works. So basically, as an engine testing, if you are in any of the engine testing department, you get what is called as test request. So basically, where does this test request originate from? Basically, you should understand that there is every company has a marketing, and the marketing is looking at what is the requirement coming from the market. So imagine for a kind of a truck company, there's a requirement saying that they need a truck for a mining operation. So they know there's a mining to be done. The depth of the mine will be, say 200 feet. So the load carrying capacity is required. All these things are known to us. So we get a test request saying, which is actually cascaded into the vehicle. And from the vehicle, it becomes an engine test request, and engine test request get to say, yeah, we need an engine of, say, a 5-liter engine, which is producing around 250 horsepower and say 900 Newton meter and meeting the Euro 6 emission norm. So that becomes a test request. Or else it could be a different new project itself. They may say the diesel prices have gone up and we need an engine, not diesel, but a CNG. And if we don't have a CNG engine, probably it becomes a new project where we develop a new CNG engine. So once we get this request, it is usually handled, as Professor said, it is handled by a design team. While I also had a design team myself, I developed in the recent past a 5.3 liter and 8-liter engine for heavy duty truck. So the design team will sit down and start making the architecture that is required to meet this performance requirement and other requirements on an engine. So when this requirement is done, that flows into the testing department where we do the hardware that is selected by the designer is been procured, and then we make the first prototype engine. So that's the second box, the activity that happens. So once the engine is prototype ready in the testing department in the proto assembly area, this engine is moved to what is called a test cell, which is a complete setup of equipment for measurement and also dynamometers to load the engine, where we really optimize an engine to the required performance levels. So what we do in the test bed is covered in the fourth box. So what we do here is, I will use a pointer probably just to make it more clear. The pointer is seen, yeah. So what we do here is the test cycle and data is generated in the test bed. That means engines are run at different cycles like full throttle performance, part throttle performance. Engines are run on various emission cycles like world harmonized transient cycle, world harmonized emission, steady state cycles, and a lot of data is generated. But data is generated, but you need to analyze this data. So we have a set of people who actually process this data and also start looking at making report and seeing that whether it is met the request requirements. So these are all the things that is done here. And if this is not met, we go to the next area where we actually start either tweaking the hardware that we have selected might need some tweaking, or we go with the further optimization of engine to meet the final requirement. So this becomes the heading of testing process overview that I gave it. So now let us look at what happens to a testing guy inside the engine testing department. So you can see I've just given it kind of a typical example. You see, I'm from Ashok Leyland. So basically, if I'm a testing guy, how do I look at engine testing? If I was say in Tata Motors or Eicher, then how would I look at the same engine development? So if I'm in truck industry, my primary goal would be to meet the higher load carrying capacity. That means I'll be optimizing engine for carrying the torque that the developers are required to carry the given loads of the vehicle. And also because for a truck, 60% of the operating cost of a truck is usually the fuel consumption. So we have to be very careful in getting the better mileage for every kilometer, every liter of the diesel that we are burning. So the other requirement is anyway driven by the government. So and the present condition, from 2020, any engines that we are making for any application has to meet the Euro 6 application or the BS6, what we call it. So if you are in the car industry, you see the requirement totally changes. Here the interest is how to get higher power, comfort levels, that means low NVH kind of a thing, noise, vibration, harshness, that would be the target. From the legislation point, again, it is the BS6 complaint that would be required. So that is how you see the same engine testing going between two kinds of different requirements which come to a testing engineer. But ultimately, what he does back in that, he measures power, torque, and emission optimization is the work that happens in the test. So now we go, what is the importance of engine testing? So basically what we do, we are actually optimizing the first and foremost to get the required power and torque, because that's the prime important. If you want to propel the vehicle at a certain vehicle speed, because that's what the driver gets and the feeling for which he buys a product. So we may have to make sure that the hardware that we have selected and the fuel injection optimization or the combustion optimization we do will give us the required power and torque. The next requirement, as you know from the legislation, we have to validate whether this engine meets the the required legislation. In our case today, it would be BS6. So once when we are doing this to work, we capture a lot of real working condition of the engine, and we capture this data. We keep on modifying the data set or the optimization because it's all an electronic engine. And ultimately, we try to meet the required performance and emission aspect. So while we are doing all these things, you might be wondering that engine is all being done in the test bed. What happens to when it will perform on the vehicle? So what we do other way around, we also capture the data of these vehicles performing on the field. Say this vehicle is operate, say somebody wants a bus which is operating from Mumbai to Delhi. So we know what is the average speed that are required. We know the load carrying capacity. We know the acceleration that would be required. So we actually try to get that information from the vehicle road load information and make sure that the engine that is developed here with the required emission is also going to meet the required performance on these kind of duty cycles that that vehicle would be ultimately pitched into the market. So once you know that these things are done, there is other thing, geography, because geography, India kind of a country is a big geographical location. So altitudes are different. When you go to the northern part of the country, I myself have gone and tested vehicles even at the altitude of 16,000 feet above the sea level. So what happens is this kind of altitude, the oxygen contents are lower, air density is lower, the power will get reduced. So we need to optimize the engine for high altitude application. In a similar way, India being a tropical country, we have peak summers and also peak winters in different geographical. So we should make sure that also our engines can start at cold startability conditions, say 0 degrees or -15 or -25, depending on the geography. So we need to optimize the right hardware and the startability conditions of the engine. So you can see under the importance of the engine testing, broadly, we do all these things to ultimately optimize the engine before it is offered for the vehicle testing, where as a vehicle, the engines are tested. So now let us move to the very interesting area, which is the hardware selection and the assembly activities that happen in the testing. So what do we do here? So you can see engine as a system. Well, Professor showed you a schematic diagram of the engine. It is a similar thing, while I've used the boxes here. So engine has to have a right intake system. What is the intake system? Basically, at a vehicle level, it's the air cleaner that is there on the vehicle with a lot of hoses connecting. So if it's most of the engines are today turbocharged engines, no more the engines are naturally aspirated. So the right selection of the turbocharger, that becomes the air intake system part of that, because air turbocharger gives the required air to the engine. Then the main part of the engine is the fuel injection system. Again, traditionally, for so many years, we were all dependent on either the mechanical fuel injection system or rotary fuel injection system. But presently we are all with the modern common rail engines. So we have all become electronic. So the selection of the fuel injection system becomes very important for an engine. So these are the main subsystems. So as you burn so much of fuel, then you have to cool the engine, and most of the engines are today water-cooled engines. So how do we really do the cooling system of the engine? So basically, cooling is required to remove the heat that is generated inside the cylinder back into the cooling water, so that you can reject the heat in the radiator, which is the part of the vehicle system. And also because now it is a turbocharged engine, we have to remove the heat even from the intercooler, because otherwise the boosted temperatures are really high. So all this heat gets into the radiator and the intercooler system, which will be rejected back into the engine coolant system. So this is a very important part of the engine system that we have to optimize. Fact that all the engines today are electronic, we have many sensors in the engine, we have a lot of wiring harness connecting it to the actuators. So electric system becomes very important. No more the engines are purely mechanical components. If you had taken engines which are 25 years back, you could have not seen one sensor or one wiring harness. But the present engines have many sensors, actuators, and wiring harnesses. It's very complicated. So the next system, which is quite important, is the lubrication system. Lubrication helps us to lubricate all the parts to avoid wear and tear, and also to remove the heat from the critical areas like bearings or the crankshaft pins, and also the piston liner area, or removing the heat even from the piston by having piston cooling nozzles. So lubrication system becomes very important, and also lubricating oil has to be cooled, which is again rejecting heat, which is absorbed by the cooling system of the engine. The last system, which is quite important, is the exhaust system. These are basically the gas coming out of the combustion chamber through the exhaust manifold. is flowing down into a after treatment system. As you know, present to meet the emission norms at a Euro 6 level, we are not able to control all the emission within the engine. So we have after treatment system. So the after treatment systems have a lot of noble materials in that, like platinum, rhodium, and palladium. So these reactions have to happen at higher temperatures. So we cannot afford to lose any of the heat in the exhaust system. So a lot of insulations are done before it enters the after treatment system. So this becomes generally the overview of the engine subsystems. So let us now look at what are the real critical hardware selections that we do for meeting the required combustion and performance optimization to meet the suitable emission application. So basically, we have a turbocharging system, as I said, for the getting the required air, and we have a fuel injection equipment, which is FIE, which basically consists of fuel injection pump, common rail in the present context of common rail, injectors, and high pressure pipe, which is connecting the common rail to the injectors. You must have heard that to meet certain emission norms, we are also using exhaust gas recirculation. That means we take some amount of exhaust gas out from the engine and again put it back into the combustion chamber, which I'll explain later. But that is one more thing. We do a lot of hardware selection to get the right side of EGR cooler and the valves for that. And last but not important, but last but most important is the after treatment system, which basically consists of a DOC, which is diesel oxidation catalyst. It has got a DPF. These are basically, when I'm talking, this is for a diesel engine. This has got a diesel particulate filter. Then we have got something called selective catalytic reduction and an ammonia skip catalyst. So all this hardware selection has to be properly done for a given engine and married it properly with the proper combustion activity. So let me go to the interesting topic, which I think you must all covered in your thermodynamics, is one of the mechanism to get some of the energy back from the exhaust to do a real work would be a turbocharging system. So the exhaust gas which is flowing out to the engine is at a very high temperature, depending on the size of the engine. It's roughly around 650 to 720 degrees. So we are connecting it to a turbine housing where it rotates a turbine at roughly around an RPM of 125 to 135,000 RPM. On the same shaft of the turbine, we have connected a compressed wheel here. So the air from the fresh air from the air cleaner moves into the compressor. It gets boosted to a higher pressure, and the boosted air picks up a lot of pressure and temperature. So the temperatures can go up from 140 to 180 degrees centigrade. So we need to cool this air. If not, we will lose the density of air going into the engine. So we have got something called as an intercooler here. So the turbocharger basically helps you to boost the intake air into the engine, and thereby we can increase the specific power output of for a given cubic capacity of an engine. So if I imagine you had an engine producing 100 horsepower from, say, a 4-liter engine, with turbocharging, probably you can go to 130 to 140 horsepower by turbocharging. So here, left-hand side, you can see how a turbocharge is working. So 9 is actually an air cleaner. So the fresh air that after all the particles are removed is going into the compressor here. As the exhaust gas is rotating the turbine here, the compressor compresses there. The compressed air is going compressed into the intake manifold and then back into the engine. If you want an intercooler would be fitted in between so that it cools the air. So what does the turbocharger selection is important in engine testing? Because turbocharger selection is important to us because it helps us to get the right airflow, boost pressure, and the transient response. You must have noticed that from the latest cars, anyone of you are driving or any of your two-wheelers are not there with the turbocharging system, but the higher end should be having one. So the transient response is quite fast. If you can see in a car, just when you floor the pedal, the vehicle is able to propel very fast because it is able to develop the required power within a few milliseconds or microseconds to get the required boost pressure. So basically, you get the required air mass flow. Boost pressure is one of the critical input which impacts the performance emission. So to meet the required emission norms, turbocharging becomes quite important because you need to have the right air-fuel ratio inside the combustion chamber to meet the emission requirements. So this is same thing schematically I've given just to say that in a compressor, fresh air goes, it gets compressed, and that air is now fed into the engine. And from the turbine, from the exhaust manifold, you have hot gases coming, which rotates the turbine, and you usually, if it's entering at around 600 to 680 degrees, we are converting into an energy, and the the temperature drops to around by 100 degrees across the turbine housing, and the exhaust gas is then fed into the after treatment system to treat it properly. So the next thing for you to little bit get more deeper into the turbocharger, how do we select the turbocharger? So if you want a higher horsepower engine, say for a car application, then we would like to have a higher airflow at higher speeds, which means what we try to get a larger volume turbine in a compressor housing. But because it's a larger in size, when the engine is running at a lower speeds, probably you start losing the airflow in the lower speed. So there's a compromise. When you want a higher horsepower, you get at higher speed, but your low end torques will drop. But for a higher torque application, say imagine if you want a truck application, our idea is to get more torque at lower end speed and mid speed, because a truck vehicle will be fully loaded in a truck, say 55-ton truck has to move in the first gear at a very low speed. That means you need a very high torque at a low end speed. So if that is the case, we have actually selecting a smaller volume turbine and a medium volume compressor to meet this kind of a requirement. So you can see there is already a compromise kind of a selection for the turbine and compressor housing between a high horsepower and a high torque engine. But imagine if you want a kind of high power and a high torque combination, then you need the best of both here. So which is normally not possible with a fixed geometry turbocharger, where the compressor and turbine wheels cannot change between a high power requirement and high torque requirement. Then we go to what is called as a variable geometry turbocharger, where the compressor and the turbine wheel, the wheel can be changed as per the speed requirement at a higher speed or the higher torque requirement. But it's expensive compared to a fixed geometry. But that's also one of the selections that we do while marrying an engine with the right turbocharging system. So we'll move to the next system, which is quite important, and that is the fuel injection system. So fuel injection system, FIE, consists of usually a fuel injection pump, which you can see here, and a common rail. That's the latest, there's a rail here. That means when the pump, which is rotated by the engine, compresses the fuel from the tank to a very high pressure in the range of 1600 to 2000 bar, and you have a fuel that is available in the rail at 2000 bar. And from the rail through a high pressure pipe, we connect to an injector. And with these injectors are usually solenoid type of injectors. That means from a ECU, we can program and tell when to open and when to close. And thereby we can inject a very high pressure fuel into the combustion chamber, and we can get a better automation. So that's the function of a fuel injection pump. So fuel injection pump, fuel injection is also, a pump is also selected based on the fuel delivery capacity. So you want 100 horsepower, 200 or 300 horsepower. We know what is the kind of a fuel delivery required through the injector. So the sizing that is done is as per that. For an example, just if I want 300 mm³ per stroke, then I need a different kind of a pump compared to 100 mm³ per stroke. And also if I want a higher injection pressures, say from 1800, 1600 bar to 2000 bar, then also the sizing of the pump is also quite important. So that's how we do a selection of the fuel injection pump with respect to the fuel delivery quantity and also the injection pressure. Now we go to the main part of it. How do we select the injectors? Injector selection is basically selected to see how much should be the through flow, means how much quantity you want to deliver per cylinder per stroke. So here what we do is just to give a typical number depending on the size of the engine. We have from 800 or 500 to 1000, 2000 cc per minute kind of a flow. So how will we do it? That is basically done by the sizing of the holes in the injectors and also the diameter of holes. Just to give a typical number, the modern diesel engines, the number of holes could be from 6 to 8 holes, 9 holes per injector, in the diameter ranging from 0.12 to 0.16. So those are the fine kind of a manufacturing that are required to make this common rail diesel injector. And the last point is the spray angle. The angle which the fuel is sprayed into the combustion chamber is also important. So all these are the things which we decide before in the proto engine, in the design stage, and also when the engine is built before we go to the test bed to optimize the engine. So the next important hardware selection which I covered was the exhaust gas recirculation. So as you see in the schematic on the right hand side, the exhaust gas which is coming from the engine gets filled up in the exhaust manifold, which some part is going to the turbocharger to rotate the turbine, and the circuit was explained to you before. But we will now go to the right and see how do we get the EGR gas into the engine. So basically on the exhaust manifold, we tap through a pipe, but in between we fix the EGR valve, and the exhaust gas, the required quantity is treated by the EGR valve, and that exhaust hot gases, which is around 600 to 700 degrees here, is made to flow into the EGR cooler, because if otherwise 700 gas go enter into the engine, thereby replacing the mass flow, that air that is fresh air getting into the engine. So we cool it a 650 degree gas to as low as 180 degrees before it is fed into the intake manifold. The compressed air from the turbocharger is coming here, and both the gases, and then it gets to the cylinders. So what we do here is, because the specific heat of the exhaust gas is high, it will lower the combustion temperature, and also the nitrogen content increases. Nitrogen will react only at high temperature. So, we actually start cooling the combustion chamber, and this will control the NOx. NOx is usually a byproduct of high temperature and pressure, high temperature combustion. So that's why we are trying to cool it by an EGR kind of an selection. So here what happens, the EGR valve selection, the valve diameter, all these are a selection, and also EGR cooler capacity. Based on the flow rate, say if you want around 150 kg per of EGR that is flowing, then we have to have the right size of EGR cooler to cool this gas before it is fed into the intake manifold. So now I've finished the hardware part of the selection. So now let me move to the interesting part, which you might all be waiting, is how to get into the test set. So you must have all been in the labs, in your own labs, where you are testing some of the engines and getting some of the data. But you can see these are large labs within the company where we are testing the engine for various required for emission, performance, and also durability. So basically, the center, what I've shown is a schematic of an engine, and to load an engine, you need what is called a dynamometer. I'll be covering that in the next part. So here, what has happened for engine, you should all consider that now the test bed is inside where it's not on the vehicle, so you don't have an air draft coming to cool any of the charge air cooler or the fuel which is there. So we need what is called a fuel temperature controller. We need to cool the water, so we have the water temperature controller. Charge air cooler in the vehicle is air to air, but we don't have an air draft here, so we have an air to water charge air cooler. So one more thing which you should understand is, as for the testing condition is concerned, we need to get the right intake, condition of the air into the engine. That what I mean to say is, depending on the condition, we need to, depending on the place where the testing facilities are there. Say I'm at a altitude at Hosur where I have the facilities around 900 meters above the sea level, and the barometric pressure is 913 millibar, while for STP condition of testing, it should be at 1000 millibar. So we have air conditioning system will pressurize the air at 1000 millibar, control the temperature is 25 plus or minus 1, and also controls the humidity at around 55 plus or minus 10%. So we have a big air conditioning system which is supplying the air during the engine testing. Similarly, the exhaust gas which is coming, we have to measure a lot of emissions. So you can see, as I said, after treatment as a DOC, DP of SCR and ASC. So we measure the smoke, opacity, gas analyzer, because we are using ammonia to injecting ammonia for reduction of NOx. We have to measure if there is any ammonia slip. So we have ammonia slip emission analyzer, particulate matter system, and also particulate counter. Nowadays, we measure the size of the particle. So you can see the test bed is so complicated, including the fuel bits which are there and the control system to control the dynamometer. So just to give you a typical number, for a size of 400 kilometer dynamometer with all these systems, what I've shown you would cost between 5 to 8 crores of rupees for all having all these things as a system. So now let me go. I just schematic things I've just bucketed here to show which are the few equipments where it helps for performance measurement, some equipments for emission measurement, and some of other test and control equipment. So you can see for performance measurement, for speed, torque, power, you have a dynamometer, airflow meter, fuel flow meter. You need a lot of pressure and temperature sensor. Also to measure in-cylinder pressures, you need a peak firing pressure sensors. So when we come to emission equipments, we have gaseous emission like CO, HC, NOx, and also particulate matter. Particulate matter is basically PM, what we call. And also we have to measure any of the gases passing to the piston rings, which is called a blow-by gas, which goes into the crankcase and then it comes to, if you leave it outside, it goes to the ambient. So we have blow-by meter. So what are the test cell control equipments? Basically, as I said, air conditioning system to measure, maintain the required air condition in terms of pressure, temperature, and humidity. We have a dyno control system because the dynamometer has to be controlled properly to give the required load to act as the same thing, how the vehicle would get loaded in the vehicle. Fuel temperature controller and water temperature control. So I bucketed the same schematic diagram in the previous year to get an idea. So many kinds of equipments are there. What does it mean to engineers here? People who are in the electronics, you can see that each of these has different principle, which I'll be showing you later. Who are into mechanical engineers, you can see these are the various equipments that would be required to measure the torque and power and things like that. So let us now go to the next topic. In the next few slides, I thought I'll also cover, while I talked about equipments, I also thought because it's a practical session, we are also to understand how of each of these equipments on which principle it works. So basically dynamometers are in two categories. Some are passive dynamometers and some are active dynamometers. What are passive dynamometers? Passive dynamometers are usually eddy current and hydraulic dynamometers, where it can absorb the power of the engine and dissipate as heat, and it could not motor the engine. That's the difference between a passive and an active. In an active motor, actually, you can make the engine also be driven by the motor. That is basically, we want to simulate when the vehicle is going down the hill, usually the weight of the vehicle or makes the inertia of the vehicle makes the vehicle to drive the engine, and that is where we want to simulate in the dynamometer. We cannot do that with an eddy current or a hydraulic dynamometer, and we want what is called an active dynamometer. And also in the latest emission legislation of Euro 6, we need to run transient test cycle. That means every second we need to change the speed and load of the engine, which I'll show you later. And hence the present dynamometers are no more passive. All the Euro 6 testing needs an active dynamometer. So basically, this is an active dynamometer which you are seeing here. It's quite a large and expensive equipment. So just to give a number, if a particular size of an eddy current dynamometer would be 25 lakhs of rupees, a transient dynamometer of a size of for a similar would cost between 1 to 1.5 crores of rupees. So it's quite an expensive equipment. But why we need that? We can brake and load an engine. That's the use of a dynamometer. And to run an engine without firing, that means we can motor an engine. So basically, an active dynamometer working principle is a three-phase AC motor. So changing the current, we can change the torque, and by changing the frequency, we can change the speed. So that's the principle on which the active dynamometer works. So now dynamometer is to load the engine, but how do you measure this load? So basically, there are two types of load cell for torque measurement. Some are load cell based measurement and some are torque flange. So load cell are basically a Wheatstone bridge which is fixed onto your outside stator of your dynamometer, which is seen here. So as there's torque applied on the engine, the stator turns to move, and there's this load that is coming on the load cell, and because of this Wheatstone bridge, we can make that, and if you calibrate it properly, we can know how much torque this engine has produced. In a torque flange method, you have a torque flange. That means the shaft itself has a strain gauge which is fitted, which makes you to, by the principle of non-contact virtual signals, and with a divisible antenna ring, we are able to measure directly the torque on the shaft. So these are quite complicated compared to load cell, but we have dynamometers which have a torque flange based torque measurements also. So let us now go to the eddy current principle. So basically, it works. The dyno, when the engine is, it has basically got by changing the primary current, you are changing the power of the magnetic field and control the torque load applied on the engine. So by supplying a required eddy current into the stator, you can create the load on the rotor, which is fixed to which is connected to your engine. So similarly, for a hydraulic dynamometer, it's a water braking power. So we are actually with a running paddle wheel on the both the side of the mounting and rotor. We are able to apply the required torque by changing the water quantity that is getting into the hydraulic dynamometer. But basically, in both the dynamometer, you actually land up converting the torque that is by dissipating the heat into the water. So that's the principle on a eddy current and a hydraulic dynamometer. Torque principle, you can use most of these dynamometers use load cell, which is connected as you see in the side of the dynamometer to measure the torque. So now we'll move on to some other equipments which are in the test bed. As I said, we have a fuel temperature controller. So I'm just now also putting the numbers why it is required. For measuring the standard test condition, you need to maintain the fuel temperature. In a vehicle, what happens? The fuel tank is exposed to the ambient air. So the hot return fuel which goes from the fuel injection pump, which is not got injected into the engine, is getting back because it is already compressed very high. The temperature would have increased. It goes to the tank, and because of the surface area of the tank and the air draft in the vehicle, the fuel temperature gets controlled. But in the test bed, we have a fixed system. There is no air draft. So to maintain the fuel temperature, we have a fuel temperature control because our standard test condition says that we have to measure, keep the fuel temperature as 37 plus or minus 2. So what is the working principle in this? We have a refrigerant which cools down the liquid coolant, and then the fuel through a heat exchanger, we are supplying the hot fuel which is coming back from the engine. And by adjusting the solenoid valves, we are able to control the fuel intake temperatures. The similar for water temperature control, also based on the manufacturers, we set the water temperature at 85 plus or minus 5, or we can set to any temperature between 85 to 95 plus or minus 5. Basically, it's a heat exchanger. That means the hot water from the engine is going into heat exchanger tubes, and we have a cold water which we are supplying outside. The quantity of the cold water supplied will control the water temperature in the heat exchanger. Thereby, we control both the fuel temperature and water temperature during testing as per the standard temperature and pressure requirements that are required to maintain during testing. So this is quite a thing which you might have not seen most of in the labs that you are doing. This is quite important. If you are supposed to test an engine at a higher altitude and a sea level, there's a lot of difference because the air density will change, and thereby the breathing capacity of the engine will change. To that same extent, the power developed by the engine would change. To have a standard conditions, we have an air intake conditioning system which basically has large capacity blowers, which will compress the air and supply it at 1000 millibar, depending on the airflow that is in the requirement. In this case, this equipment could supply you up to 2400 kg per hour airflow requirement. And you can see it is also controlling the required temperature at 25 plus or minus 2, and also relative humidity. So now how the relative humidity is controlled is, if the humidity is low, we have got steam injections inside this equipment, which will inject steam to increase the humidity. If you want to decrease the humidity, if it's a rainy season, then automatically the heaters will switch on and it will maintain the required humidity. So thereby, these equipments are usually not inside the test bed. These are all kept above the test bed, and it is connected through the air ducting system into the engine. So you can control the air that is going to engine with an air conditioning system. Next, in any testing, and there's also testing in the labs, you might have seen that we have to measure various temperatures, like air intake temperature, exhaust temperature, boost temperature of the CAC. So what sensors we use? So usually we use PT100 for lower temperature range, and thermocouple up to 1000 and above up to 1000 degrees. We use K-type sensors. So basically, what is the working principle for a thermocouple or the K-type is basically it's working on a seeback effect. When there is any conductor, such as a metal, is subject to a thermal gradient, it will generate voltage. And this voltage is measured and converted into a temperature value through certain small electronics like indicators, where we calibrate with our hot bath. We physically keep the sensor in a hot bath and we check if 50 degrees it is able to control, show 50 degrees, or we are able to adjust the microcontrollers to give that temperatures on the indicator. So once it is ready, then we fix it on the engine, and then we can integrate these temperatures to our control system, and we are doing the engine operation. We can measure the right temperature the engine is developed during the operations. Similarly, PT100, you can see that it's made of platinum and has a specified resistance of 100 ohms at 0 degrees. And by accurately calibrating the resistance to the temperature, you can also use it for the low temperature. Where air intake temperatures might not go more than 50 degrees, then we use PT100, and for all exhaust temperatures and boost temperatures which are higher, then we go for a thermocouple type of sensors. So similarly, like temperature sensor, we also need various temperature pressure sensors. Reason is we want to measure intake depression. Intake depression is usually a negative pressure because you are sucking air into the engine. But when it's a boost temperature, boost pressures, then it is quite high. Boosted air from a turbocharger can go up to 3 bar absolute. So then we use the right pressure sensor. So how does a pressure sensor work? Basically, it's a capacitive pressure sensor operates on a principle that if a sensing diaphragm, so you see a diaphragm here. So it is between the two capacitor plates here. And by the deformation of the differential pressure on the imbalance of the capacitor will occur between itself and the two plates, you can see here. And this change in capacity is measured using a bridged circuit to measure the pressure in the system. So this is typically an textbook thing, but there are various methods on which the pressure sensor works. So, but typically these are the temperature ranges we select, and also I will show you where each of these temperature and pressure sensors are used in the testing. So now there is one more sensor that is required is humidity sensor. So the humidity sensor works on a dielectric property of a polymer film. Depending on the amount of water contained in it, as the reductant changes, the dielectric property of the film changes on and the capacitance of the sensor. So we also use humidity sensors that are spread to read the humidity. So you can see whatever I showed in the last few slides are each of these equipments which have got the principles on it, which works. And later I'll be showing emission also there. Some are also chemical reactions are happening to measure the required data. So you can see now I showed you a lot of sensor, but where is it used? So you can see here one air intake pressure, temperature, and relative humidity. You can see this is the air cleaner. So wherever the duct that is connected, we put all these three sensors which measure the pressure, temperature, and the relative humidity. So out from the air cleaner, you know it's an intake depression because the turbocharger is sucking here. So you need a air intake temperature and air intake after the air cleaner, and also the depression. So there's a pressure sensor and there is a temperature sensor put here. So here you can see a relative humidity is also measured. So after the turbocharger, you know the air is boosted here. So you need boost pressure temperature, and boost temperature also. So you have fixed two sensors here. After the boost air goes, it goes to the intercooler. Then there's a temperature drop here. So we are fixing a boost pressure. There is some amount of pressure drop because this is basically a heat exchanger. There may be 100 to 150 millibar drop here. So we measure that, and we should know this because we have to calculate the right amount of airflow. So inside the manifold, we also drill holes and put the real temperature and pressure. So basically, on the exhaust side, you can see we again have a boost exhaust gas temperature and the pressure. So you can see typically, you might have wondered where these sensors are used. So we need all these temperatures and pressures because with this we can make a lot of data analysis and say whether it's running properly, is it developing the right torque. So where there are various calculations and data analysis that we do that. So the next one, what we are moving here is fuel meter and airflow meter. So these are also quite important. Fuel meter, in this case, we use not the fill method that you must be using in the lab. We have pyrolysis principal fuel meter, which helps us to continuously measure fuel every second. Airflow meters are also we moved from the old turbine airflow meters, and we are using ultrasonic transit time differential techniques to measure the airflow. And here is the blow-by meter, which I talked about. Blow-by gas is basically the gas after the combustion. Some of the gas cannot be sealed completely by the piston rings. So this gas actually escapes to the piston rings and go into the crankcase. So these blow-by meters are actually working on differential pressure sensor principle, and we can exactly measure the blow-by gas. The blow-by gas, depending on the engine sizes, could be varying from 60 LPM to 105 LPM. So these are the gas we need to control because they will carry some amount of the oil back into the atmosphere. This is quite interesting, and I think some of the labs in your experiments will be actually having a combustion analysis. What we are actually doing, we are drilling holes into the combustion chamber and trying to measure directly the pressure that is developed in the piston, the fire when the combustion happens. So this is basically for your thermodynamic lab to draw your P theta or PV diagram. So we can have this sensor into the combustion chamber, and in the engine we put a crank angle encoder. So for every degree rotation, we exactly know if we match that data with the pressure data, we exactly know how the P theta or the PV diagram can be put. And all these signals from the sensors are captured by the amplifiers here, and then we can get all this information from the combustion. It's quite an interesting and expensive equipment, but if you really want to do a research level experiments, then you need such kind of an high accuracy sensor, which basically it is working on a piezoelectric pressure sensor. So before touching of the emission, I just wanted to give an idea that a perfect combustion would be that you have an hydrocarbon, which is a fuel, air as oxygen and nitrogen. You should have got only H2O, CO2 and N2, but that is never happening because of the high-speed nature of the engine. It's very difficult that all these are happening perfectly. So the imperfect combustion happens and the byproduct is usually nitric oxide, CO, HC and particulate matter. So just next slide is again to touch upon to say what is the why we are all worried about each of these pollutants. You can see hydrocarbons can create photochemical smog, lots of lung disease and also damage to vegetation. Carbon monoxide is basically a poisonous gas, as you know, but it could reduce oxygen carrying capacity of the blood and prolonged exposure can cause no. Nitric oxide, as you might have seen, everybody are really worried about the NOx engine. That is basically because it can cause photochemical smog, acid rain, and many of the high emissions that you might be seeing in the cities all because of the oxides of nitrogen. Particulate matter, it's a big problem, as you know, from a diesel engine. That's why people are measuring, and you can see this numbers. PM 2.5 has to be within certain kilo levels, or if not bigger cities, you know, they go to close down where they stop the traffic. So it leads to poor visibility, and it has a lot of highly carcinogenic components which can cause cancer. And you can relate this why many of the people, even it's not hereditary, are getting cancer is because of the particulate matter. So this is the typical thing you should see. This have actually shown an emission legislation of diesel engines. So you can see when I started my career way back in 1996, I was at 18 grams per kilowatt hour NOx. And today you can see at BS3 or Euro 3, what we call Euro 4 and Euro 6, you can see these cycles, which I'll be covering. This is the European steady state cycle. They bought certain cycles which are closer to how the vehicle would operate in the field. And for this, actually, you need a transit dynamometer. And you can see this number, which was 18, became 5, 3.5, 2, and now the engines which we did in last year development, all we have reached to 0.4 level. And you can see each of this number, if you seeing from where it started, the percentage at which we have really dropped is almost more than 95, 99%. So CO, which was at 14, has gone to 1.5. Hydrocarbons from 3 point, we are at 0.1, we are 0.16. This is only two different cycles here. Particulate matter, which didn't start, but has started in the Euro 1 level at 0.3, but you can see here at 0.01 level. At Euro 6 level, which was not asked up to Euro 5, was particulate number. So today, logically, if you come in our lab, we are having very sophisticated equipments to measure the size of these particulates. So that is controlled at a level of 8 into 10 power 11 for WHHC cycle and 6 into 10 power 11 at WHCC. Because we are using to control NOx, some ammonia or the commercial name is AdBlue. If you see in the latest vehicle we are carrying, other than the diesel, we are carrying something called AdBlue, which is basically ammonia. So as we are injecting into the combustion, some can pass to the the catalytic converter. So we are controlling that also at Euro 6 level. This should not be more than 10. So here quickly, I will not go into much of the theory. Left-hand side diagrams are all showing the schematic diagram of how a gaseous analyzer. So the principle on which a gaseous analyzer for measuring NOx works on chemiluminescence detection. So there are a lot of chemical reactions that are happening. We are giving ozone and the gas goes inside it, and then we are able to convert a photo counter, will say how much NOx is coming. For hydrocarbon, we have a flame ionization detection principle. So we have a flame, the hydrocarbon from the engine which is getting inside will burn, and there are a high voltage ion collector to measure what is the real hydrocarbon produced in terms of ppm. Similarly, for CO2, we have non-dispersing infrared NDIR absorption detection measure principle. Quite complicated, lots of electronics in that, which is shown in the left one. OT is basically by a paramagnetic detection principle. So I just give an idea that the emission system also has a lot of complicated electronics systems, and these are quite expensive. Similarly, here, next slide, I'll show what is the equipment, but basically particulate matter, you can see if you take a filter paper and see what is in the particulate coming out. It is a lot of lube oil which escapes the piston ring, some of the fuel which is not participated in the combustion, sulfur which is in the fuel, and some of the inorganic solubles like metals which are available like zinc and other things which are available in the thing. And carbon is basically the final product of your combustion, which also is a part. So your particulate matter, so all this pollutant in that which we are getting out of the filter paper here, this is a particulate here, which is usually we divide it into solubles and insolubles, but anyway, we collect this. We try to attack each one of them in our combustion to reduce the particulate matter. But now the interest is to see how do we collect this. So we have an equipment where we take a sample gas from the exhaust and we dilute it like how it gets diluted in the ambient air. You should all keep in your mind when the exhaust gas get out of the vehicle, actually it mixes with the complete ambient air. Bigger particles started settling, smaller are the ones we don't settle and keep on in the ambient air. And that is where which gets into your lungs and creates problems. So same dilution we do with our equipment here. You can see we do the diluted here exhaust sample and collect all the sample paper during this particular cycles like WHSC or WHTC, and then we measure depending on the power out of the engine, we really measure and say how much grams per kilowatt hour of the particulate is produced from that. So next is opacimeter. Basically, opacity measure the smoke levels of an engine. It works on B-Lambert law principle. So you can see there's a detector here, there's a lamp here. The soot particles which get into the thing, they will not allow all the light to get into this detector. So the reduction in the light is indirectly calculated as how much is the opacity of that gas which is produced at that instant in the diesel engines. So now let us go to the test cycle. Before that, now I think I've covered something like what are the equipments, what the test bed looks like, everything. Now you see now the engine has to be run. Now let us go to the practical. So you are started the engine, but you cannot start the engine like that, but you have to keep all the boundary condition first, because testing an engine without meeting the required boundary condition is like you never can repeat these experiments again. So to repeat the experiments, the engine is connected to the dynamometer. So as I said, now I bought all the equipments in this schematic. So fuel is maintained as 37 plus or minus 2. Water temperature is controlled as 80 or 95 plus or minus 5. Intercooler temperature usually, because you, as I said, booster temperature will be around 160 to 180 degrees. We maintain it at 47 plus or minus. This is actually seeing at what the vehicle system is able to maintain. The vehicle intercooler is maintained at 50 degrees, then we maintain at 50 degrees here. So the pressure drop across the intercooler is maintained, in our case, a typical example around 110 to plus or minus 10 millibar. As I said, air intake condition is supplying air at 1000 millibar, temperature at 25 plus or minus 1, and also relative humidity at plus 55 plus or minus 10. So, and also the air cleaner, you know, if you have an element which is very choked, then you will have a lot of restriction here. So we put a clean element and we operated at 35 millibar and not more than 70 millibar, which is indicated the choke limit of an air cleaner. So the next is the exhaust gas. Like while you are pressurizing the air at 1000 millibar into the air cleaner, we should also make sure the exhaust gas coming out of the engine is also restricted at 1000 millibar. So we have equipments which will maintain this pressure at 1000 millibar. And this restriction of the after treatment will create certain back pressure. In our case, because of the after treatment, it can go as high as 300 millibar. But this condition, whichever I showed the numbers, have to be maintained during the complete development of the engine, so that every time you make the changes against this boundary condition, we know whether the performance has increased or decreased, or it is maintained the same. So this is what is called a setting of the boundary condition. So if you're going into a lab for engine testing, first question you should ask is, what is the boundary condition I have to maintain? Unless you don't know the boundary condition, you will not be able to. And each of these boundary conditions are coming from the vehicle architecture. Like fuel temperature, how much is the fuel temperature you can maintain in the vehicle? That is what comes here. How much is the air intake depression that the vehicle air cleaning system can give? That's the same air cleaner we have to bring here. Then we do a right proper test. So basically now we go to the real thing. So in the testing, what we have is something called as a full throttle performance, or when the throttle is pressured 100% and part throttle performance. So when you are in the vehicle, you must be seeing whether you're two-wheeler or a four-wheeler, you're pressing the act pedal or the acceleration pedal. So usually you don't floor it every time fully. You are pressing lightly as per the demand load that you want and the speed that you want. So we do the same thing in the testing, which is called as full throttle performance, to see the full potential of the engine, and we also map the part throttle performance. When it comes to emission, as I said, there are 3 different cycles on which the emission has to be done to prove. One is called the World Harmonized Steady State Cycle, WHSC, World Harmonized Transient Cycle, WHSC, World Harmonized Not to Exceed Cycle. Basically, this cycle is to check what will be the engine emission at higher altitude up to 82.5 kpm. So we have systems where we reduce the intake pressure, or else we to see what happens, because as the air mass flow reduces, there are certain combustion parameters which will change and the emission might not be the same, but the legislation authority would like to see whether we are able to even maintain this kind of emission during the emission. So here is an idea, what is an idle speed? So idle speed is when you start the engine will settle to some speed, which is actually without vibrating engine will be at some stable speed. It depends on a kind of an engine. For a diesel engine, we target to a 600 plus or minus 25 RPM. Fly-up speed is the maximum governed speed the engine can go. That means when the throttle is 100% and there's zero load, then this engine could go to, in this case, I'm showing 2500 RPM. For a gasoline engine, this could be higher also. So these are the typical thing. We make sure that first engine is stable at idle and a fly-up RPM. Now, what do we do? What is called a full throttle performance? If you want to understand what is a full throttle performance. So driver is moving his pedal 100% here. So what we do is from fly up to idle, we check. And then what we do, we on the dashboard, we start loading the dynamo. Means the throttle is kept 100%. We slowly start loading the engine. So we see how much torque the engine can produce. So I will be showing these numbers later. So that is how we do that, and we exactly measure the power and torque across the complete speed of the engine. So we keep on increase the dyno speed till it drops the minimum operating speed of the engine, and we are able to measure various parameters like what is the maximum exhaust temperature, peak firing pressure, all these parameters. So this will make sure that the design capability of the engine is met, is actually tested during the full throttle performance. So similarly, what we do is we also do in the part throttle performance. That means what we do here is we actually set the dynamo to the full load, and then we keep on changing the throttle pedal. That means we throttle pedal will be 100%, then we'll switch out to 90%, 80%, 10%, and we see how much is the torque produced and all the other parameters. During this, we measure the smoke boost pressure, and then we can analyze the complete. Why we do part throttle performance is to make sure that the complete operating speed of the engine, we should have a data how the engine is behaving. So then what happens in a vehicle when they buy damage demanding a part throttle or full throttle performance, we know whether the engine can produce the required power and torque, so that meets the vehicle requirement. Okay. So now we will go and see how do we map an engine's operating, how do we do the engine mapping. What I mean to say is, while we have to do the emission cycle, we have to actually completely map the engine. So that means in our software, we make to sure that we start running engine from an idle to full throttle and capture the data, what engine is producing at every RPM. At 8 RPM plus or minus 1, we record the torque and the speed and we save it. And then what we do is, you can see here, the WHSC cycle says the first mode has to run at 0%, zero speed and 0%. So you have to make sure that it is a normalized speed, where they say mode length, they have given time in seconds have given. So total time is 1895. So second mode, it has to run at 55% of the speed of that engine and to 100% of the torque that is produced at 55%. That's why we have mapped the complete engine speed. So once this is done, automatically it takes the data from the data that is generated, and this 13 mode is generated by the software, and automatically engine is running through this WHSC cycle, and we measure all the emissions that are emitted by the engine, and with a certain calculation depending on the mass flow of the exhaust, which is called G exhaust, and we know different ppms that are emitted by the engine in terms of NOx, HC, and we know what is the power produced by the engine, because all the emission calculations are grams per kilowatt hour. So how much emission has been generated for a kilowatt power? So a summation of that would say the numbers which I showed you in the table, like ultimately NOx after running this cycle should not exceed 0.4 gram per kilowatt hour. So that's an idea I'm giving, that we have to run this table at the right. What I was showing is as per the legislation, and we have to make the engine to run as per that for your engine. So it could be different for the different engine, different in the power and torque. Similarly, the next engine will be running in transient operation. You can see here the speed and load are continuously changing. You can see every second speed is changing, torque is changing, speed is changing, and you can see the emission. So they're trying to see whether the vehicle, when it's running in a real driving condition, is it able to meet the required emission. So that is a transient cycle. So I'll skip this slide and I'll go to what the next slide, what is called the world not to exceed cycle. So here this is a full load curve, and this is 30% of your engine curve. They divide into 9 zones here, and they select 3 zones out of that, and they operate 5 points in that to make sure that we have optimized even in between the emission properly and we have not cheated. That's why the legislation makes sure that the emission produced even in the complete operating range of the engine is met properly. So we will go to the next topic because I've got 10 minutes here. So I think we'll spend some good time here, which is quite interesting. And I think this is the real practical here. You might have all had a two-wheeler or a car, and you might have all talked about, yes, my vehicle is 55 horsepower. It produces around 50 Newton meter or 100 Newton meter. So I don't know how many of you have seen a complete full throttle performance. This is how it looks like. X-axis is the speed, as you see, 1000 RPM. And in my diesel engines are typically, below 3000. So this particular engine, the rated power is 2200 RPM. And the Y-axis is a torque. So in this particular engine, and here you can see Y-axis, there are 2 things. One is the torque on the left-hand side, and I've also calculated the power on the right-hand side. So you can see in this engine produced about 187 kilowatt at, or 200, sorry, it's produced around 241 kilowatt at 2100 RPM, while it has produced around 187 kilowatt at 1500 RPM. Okay. And this is the power curve. So you can see the power is slowly increased as the speed increases, the power also increases. But you can see at 1900 RPM, actually we have flattened the power. We didn't allow it to continuously go up. So this is actually designed by the right turbocharging. We actually open the wastegate and don't allow the boost pressure to increase. But we made the torque to actually flatten it up and get the right power at 2200 RPM, 240 kilowatt. So, and you can see the torque curve would look like this. What does the torque curve means? See, in this particular case, this is the beauty of a common rail engine. Even from 1100 RPM up to 1900 RPM, the torque is the same. That means when you're operating at this range, the drive will get the full torque of 1200 Newton meter. So thereby, even if he has different, he doesn't have to change gear if he's operating at this speed because he's getting a continuous flow of this torque. So these kind of flat torque are requirement a truck application because the operation usually of a truck is between 1200 to 1900 operations, and we make sure that we get the right torque. So now you can understand what I was doing in the test bed. To get this torque, it is not so easy. I had to marry a proper turbocharger, fuel injection system, nozzle size, piston, compression ratio. So many things have been done to get this kind of a torque and to get this kind of a power. So you could now see in this diagram how a typical power and torque looks like. So take your textbooks, or when you go to the lab, once you operate the engine completely in the full throttle performance, get this data, plot this way, look at how your power and torque looks like. That will give you a feeling that how this engine is driven. That's the important thing. Or else next time when you see any of the cars, you look through your net, if you see there's a car, Ferrari car, please also try to get the power and torque of yourself, plot it yourself in a graphical scale, and then appreciate how the power and torque curve of that engine. In a Ferrari engine, this speed itself will be 16,000 RPM. It's quite different than a normal diesel engine because there are high-speed engine, they need high speed there. So next is quite an interesting thing. I told you that for a research application, you need to know what's happening into the combustion here. So you can see here, this is the pressure rise diagram. So this is how the pressure is when the firing has happened at TDC. You can see in this case, the engine has reached around 180 bar peak firing pressure. So the maximum pressure that is developed inside that combustion was 180. That's the peak firing pressure. But you can see that has happened just after TDC. How did it happen? The fuel that was injected, we gave a pilot injection roughly about 30-35 degrees before, a very small quantity, and you can see the injector is closed. That has helped to warm the air that is going inside because it's a diesel engine, you are only pumped the air here. Then at about 8 to 9 degrees, we have put the main fuel that's been injected, and the injector has got closed. End of injection has happened, and that is because the fuel has come here. The complete raise of pressure has happened, and that's how you get the final pressure here. So this is a very good way that we had to drill hole into the combustion with the piezoelectric pressure transducer. We are able to measure this. Now, the next thing, what you see, airflow, because for any engine, air-fuel ratio is very important. You can see here, for 1250 kg per hour, we had pumped in 53 kg per hour fuel, so roughly around 24 air-fuel ratio has been pumped at rated speed here. But you can see in a max torque speed, the air-fuel ratio is would be you are pumped in 40 kgs, while the airflow is only 900 kgs per year. So these are the interesting things you have to see. How would be the fuel flow and airflow to get that kind of a power? So whatever you saw in the 2 slides before has happened because you are able to pump so much of fuel and air. Similarly, what happened, as I said, it's a turbocharged engine. You can see the boost pressures that have developed. The one is before the turbocharger and the other red one is after the turbocharger, but you can see roughly around 1000 here. In this case, we have produced around 1.8 bar gauge or 2.8 bar absolute. So you can see the present diesel engines are all operating between 3 bar to 3.5. Extremely high pressures are being pumped into the engine, and hence we are able to get the higher specific power output. The interesting part, which I also touched and also was the BSFC. How would the brake specific fuel consumption curve would look like? So you can see the minimum BSFC would come in the mid speed, that is between 1200 to 1600 RPM. Because why? Here the friction is so optimized and the combustion is at the very optimum region. That's why you get more here. But as you go at a higher speed, I say up to 2200, you will end up getting 222 grams per kilowatt. Why? You lose a lot of friction because the friction is increased between the piston and wheels. That is what makes you lose the friction, and that's why you reach here. So this is the BSFC curve. This is an interesting thing. What a part throttle performance I told you. What we did is we collected all the information at different throttle position, and through a uniplot we connect all the BSFC plot. You can see these plots are all connected to 205 grams per kilowatt hour and different plots. So the green regions are all that we are at a good BSFC level, and the bottom ones are not the good zones here. So by doing this, we know if your vehicle is operating in this zone, we know you get the best fuel economy. But if you're operating here, you are at the not at the good fuel economy. So now how do we optimize an engine? So what we do is, as I said, we have a lot of sensors. We have an ECU where we can control the injection timing, injection quantity, injection pressure. Then we control EGR depending on the percentage NOx reduction. We have an intake throttle valve, that is because to increase the exhaust temperature for after treatment. And there are various actuators. So now schematically, how does it look like? So engine has a crank speed sensor, cam speed, coolant, oil pressure, rail pressure, boost pressure, EGR. From vehicle, we have an acceleration pedal sensor and a vehicle speed. This goes into our ECU, and in ECU, we do a lot of processing. This is exactly work of an R&D engineer who tells for all this input, what is the actuation that you use. So ultimately, we give signal to a metering unit to say how much fuel it has to go to the rail, how much inject quantity has to go into the fuel inside a cylinder, and how much percentage of EGR has to go into the cylinder. So here I've just given the same thing, but a little bit more detail to say what do we do with each of these sensors. So air mass flow controls, measures the airflow, coolant pressure, temperature. So based on all these things into the control unit, ultimately injector will deliver the fuel, pump will deliver the fuel to the required quantity and required pressure. EGR will give the required quantity of EGR. Intake throttle will control the airflow and pressure in the common rail. So I've just actually made what I'm trying to show here is as the boost pressure increases, you see the NOx becomes positive. What I mean by positive, the NOx increases while it reduces CO, HC, NOx. So these are the playing parameters for us. So if I want lower the hydrocarbon CO, I have to increase the boost pressure. But if I want to reduce the NOx, I have to increase the EGR quantity. Fuel injection timing, if I advance it, NOx increases while other things decrease. So these are the things we start playing around. In the next few slides, I'll cover this and complete my presentation. So here in the full load optimization, this is basically a 16 by 16 matrix that we have got inside. So x-axis is speed and y-axis is actually the throttle position, and here is the injected quantity. So we inject the right quantity of the fuel for the full throttle to get the required. Just to an example, to get at 2200 RPM, 100% throttle, we have to inject 128 mmQ per stroke of this. So this map we are going to fill to get the right quantity of fuel. Similarly, we have a rail pressure control map. So you can see again it's an RPM. This is again the quantity of fuel that you have to do. So you can see if I 2200 RPM, If I want to inject 150 mm³ per stroke, then I am allowed to, this is in HPA, roughly around 1800 bar of rail pressure. I need to inject this kind of content. So you can see this map is all filled with the rail pressure that we have to maintain. Similarly, this map is to control the injection timing. You can see here at 2200 RPM, say I want to inject around 100 mm³ per stroke. Then what I do is I inject it at 11 degrees here. Probably at lower speed, you can see I'm injecting at 3 degrees. So that's the exact thing I was showing in the pressurized map, how we are controlling all this. So these are the maps that we are playing. So if you are coming into a testing department or you want to optimize an engine for any of your Baha kind of an optimization, these are the maps you have to play around to optimize it. Similarly, EGR control map, you can see 100 means fully closed. If I want, say, 25% EGR, then I open it 25%, 75 means 75% closed. And then at 1900 RPM for 100 mm³ per stroke, I can inject around 25% EGR flow, 25% opening, but the EGR flow will depend on the pressure of the gas that is available. So the last few things are like, if you want to imagine that now the fuel economy is poor here because it's quite a red zone, then what I do, I go into my map here. I find that these are the rail pressure. I am able to adjust the rail pressure and get the required opening of the injector to get the rate BSFC. Similarly, if I want to optimize the NOx here, another map. So I go to the EGR valve map and I adjust the quantity of the EGR going to make this green region. So that's how I play around to get that. So that's how, probably with a delay of around 2 minutes, I was able to complete my presentations, and hope I was a little bit fast, I know it, because of the content of my presentation. Don't look at this presentation to capture all the information I've told, but look at the complexity that is required. So when you are studying your subjects, look at each of the aspects I've covered. Your thermodynamics I've covered, fluid dynamics I've covered, I've covered a lot of electronics part of it. I've covered some of the data analysis part of it. Sensors I've covered, actuators I've covered, test bell setup. So many things I've covered. So if you are driving a vehicle today, you will be knowing that how much of work that goes back on engine development, and then ultimately it becomes a vehicle that you are able to drive with all the pleasure, getting the required performance and emission that is there. You are not seeing that, but as an environmentalist, as a legislation, we are. Thank you, and hope it was an useful presentation to all of you.
Thank you, Mr. Yogesh, for the wonderful session. Before going to the Q&A session, I request Ms. Sujata to take the flash quiz.
Yeah, thank you, Mr. Yogesh. I think it was a where treasure, I mean, I don't know what to say, treasure of knowledge is what we could say. There are a couple of questions. What is FIE system? There are questions in the chat box. Probably you can quickly answer that, then I'll get ready for the Slido quiz.
Okay, can you answer ask me the question, somebody, then I can answer it directly.
Robin, go ahead. I will get ready for this.
1 minute. I should come out of the share for you. Yeah.
Yeah, yes, sir.
1 minute. I'll do the shop sharing. Okay. Can you ask me the question? FIE means fuel injection equipment. As I said, it contains a fuel pump. Injection equipment is FIE.
And one more question also. A file system define how and where files are stored and how they are renamed.
Sorry, I didn't get the question.
I don't think that was a question. There is another question on, is there any mathematical equations for finding design parameters of engine?
I didn't get the question fully. Yes, there are for certain, if you take your design data handbook, say for design of a connecting rod, you know, you have a proper formulas with which if you have the gas peak firing pressure, then you can calculate the I section of the connecting rod. So many parameters can be done. So I think for each of the design of a component engine, there is a defined mathematics models or empirical formula wherever it is not available to get to the right design parameters.
Okay, I hope that answered to the participants who have raised the question. So to all the participants, if you see, I have posted a link in the chat box, both in the Zoom chat and in YouTube live chat. I've posted that. I do understand that a few colleges like KCG, Nanda, probably Ramco, KPR, IET, all of you are watching from the auditorium. with a big set of students arranged in your auditorium. So not sure how you're going to attempt this quiz. But however, for all the participants who are individually taking, I've given you a link. Click on the link. As soon as you click on the link, you will be prompted with a username and email ID. Just put your name and your email ID and register it with us. Preferably, the email ID has to be the same email ID as the one that you have given in the registration form.
Sujata, should I answer some of the questions which are in the chat box myself?
Yes, sir. If it is okay.
Yeah. So the other question I see is if we try to reduce NOx, other emissions are reduced. Any optimization method to reduce all the emission? It's a separate subject which I've not covered. Is usually NOx and particulate matters are trade-off. That means to say, if you try to reduce NOx, the PM increases, and if you try to increase the PM, reduce the PM, the NOx increases. Usually there is a trade-off between these two. So this trade-off cannot be avoided, but we try to manage to get to the level with the different technologies. HC, CO, hydrocarbon and CO are usually easily controlled. Hydrocarbons, we can go for higher fuel injection pressure to control it. CO by proper boost pressure or turbocharging, we can cut into. In most of the cases, only HC is measured, but there is any measurement method to identify all combination in HC emission like CH4, C2, H4 exactly. Okay. Compare as HC is analyzer wise, we have hydrocarbon analyzer, but we have Fourier transform infrared analyzers where we can measure a lot of other components of which are today not regulated. We have emission analyzers to do that, because NH3, which is we are measuring because of the ammonia slip, are measured in NDR analysis. Yes, we have analyzers for CH4 also. CH4 is basically the methane which we are measuring in CNG engines. Yes, we have got analyzers to do that. These are the only questions available in the chat box for me.
Yeah. So I have 173, 175. I would also encourage the PALS team to join, or the other members, senior members, faculty, all of you join. Considering the complexity of the session that we saw today, I think it will be a good competition if all of you also join. And the questions are all based on the slides that Mr. Yogesh sir has shown. Okay, the first question is here. Where do penguins live? Was this in the session today? Okay, you got 10 seconds to answer that. And the right answer for it is in the southern hemisphere only. Now, why was this question totally irrelevant to the session? I just wanted to give you a taste of how this works, basically. So there will be a question followed by 4 options. You choose one of the right answers, and then you'll see within the next few seconds, you'll see which is the right answer, whether it's a right answer or no. For this teasers, the trivia questions, I've given 10 seconds. But for the live question from the session, I'm going to be a little generous. I'm going to give you 15 seconds or 20 seconds to answer. So one more trivia question just for all of you to get a hang of this whole thing. The next trivia question comes here. In this hot weather, let's think about an ice cream. So any idea which country invented the ice cream first? Okay, looks like a guess it is. I don't know how many of you are answering it with some facts, but whoever has clicked on China has got the answer right. 22% of 299 participants have got this right. China is the right answer.
I suspected Sujata. Hmm?
Okay. Okay. So now if you come back, just do an Alt tab and come back to the Zoom screen. Come back to the Zoom screen and we see a leaderboard. So this is what you're going to actually see. This is just an experience of what you're going to actually do on a live quiz, where I'm going to show you the questions, post the questions regarding the session. So Radha K has got 2 on 2 correct in 17 seconds. So the fastest finger and answering the questions rightly. All that matters, and it's just not Radha. We have Lijo, Ashwin, Sri Sai, Srinidhi. Sometimes, I feel it is better that you identify yourself with the college. It will be good. I don't know whether you're all student or faculty, which college, but whoever it is, you have gone through the trivia questions, and here is the next live question, and this is going to be the questions from the session. Good luck to all of you. The first question from the session is here. Full form of WHTC. 20 seconds for the question. I hope all of you are back to your browsers. I didn't mention that. To 25 of you have attempted it, and 43% of you have said world harmonic temperature cycle, but it is the transient cycle. 29% of you have said that right. So it is very important, as Mr. Yogesh said, to pay attention to the details in the session. Moving on to the next question for 20 seconds. Okay, there is a mixed response in all the questions so far. And the right answer is active dynamometer. 22% of you have got it right. Sir, you may want to add anything here. You can feel free to add, Mr. Yogesh. You may be able to add more sense into these questions.
Yeah, okay. So actually I was telling that active dynamometers are one which can motor, because in a passive dynamometer, only it can absorb the power, and hence active dynamometers are the only dynamometer which can motor an engine. Basically, it's a motor is there, which I sold down the hill, or when the vehicle is being driven down the hill to simulate how a vehicle will drive an engine. That can be done in a motor. So that's the point.
Thank you, sir. So, try and grasp. You probably may not understand the entire session, but very relevant points is very important. Dash is a metric to evaluate an engine based on the fuel efficiency and directly reflect on the mileage. So what is that dash? Fill in the blanks. people, 266 people have responded as BSFC. And that is the right answer. 45% of you have got it right. Wonderful. Fourth question, the 20 seconds starts now. Okay, you can come back to the Zoom screen. Keep your browsers on. So at the end of 3 questions out of 6, Bharat K has got all the 3 questions right in 29 seconds, followed by Ashik, Niket, Naren. Naren, I know, is the student leader. Dasari Samuel. All of them have got 3 questions on 3 in those respective seconds. But this may not be the same status at the end of the final question. So please go back to your browsers. I hope all of you are ready. The 4th question, 20 seconds starts now. 291 have responded this as WHTC. And the right answer is WNTE. 15% of you have got it right. Moving on to the fifth question. Two 96 have responded as injector. Sir, is that the right answer? Mr. Yogesh?
Yes, sir. Yes, ma'am.
Is this the right answer? I was just checking with you, or you want to add anything to this? Yes, injector is the right answer.
Yeah. As I
49%.
said, the sensors is an input, ECU is processing it, and it acts an actuator. So in this case, all the three are sensor. The only injector is an actuator. So that's why the injector is the right answer.
Thank you. And the final question. So put your fastest finger, give a good shake to your brain. And the last question, 20 seconds here. Okay, pretty a mixed response in this. And the right answer is 100 ohms at 0 degrees centigrade. So
I think I highlighted this in my presentation.
yeah. So please come back to your Zoom screen. And the leaderboard looks like Bharat, Raji, Naren has retained, Mritul and Ashik is also retained. And question on cycle has 9 zone. I think that seems to be have been which emission cycle has 9 zones. Only 15% of you have got it right. I think that seems to be the hard question. So congratulations to all of you. This basically is the first 5 names. Probably many of you have got the answers correctly, but again, this calibrates it based on the timings also. So with this, the online quiz is ended. Thank you for participating. Over to you, Robin.
Thank you, Madam. Mr. Yogesh, we have received the questions from the registration form. Just I'm sharing the screen so you can see the questions, I think.
Okay.
So you can answer. If you have already answered, you can leave the question. So if not, you can choose an answer.
Okay. No, these are all questions, right?
Yes. Normally, we used to collect the questions from the registration form.
Okay, understood. What is the future of a slow two-stroke marine diesel engine is what you said. Marine diesel engine would continue because of the very high power output that are required. But some emission norms would come there, but it could be still managed with some after treatment system. But basically for that kind of a 45,000, 55,000 kind of horsepower, two-stroke diesel engines are the way still. But yeah, I think there are also emission legislation catching up even for aircraft and marine engines. So there are going to be improvements that are going to come. But I think basically you could still be with the two-stroke, but go with after treatment. Does BS6 engine a fuel efficient? Does it have a valuable change? Where does BS6 engine is good or to nature? Okay, the first question, our challenge was, usually when we move up the ladder for emission legislation, we actually start losing fuel efficiency. But I can proud to say that after launching of the BS6, We have measured the fuel economy of all the vehicles in the field, including our own BS3, BS4, and BS6. We find that the BS6 engines have been made more fuel economy. Valuable change, I didn't understand what is the valuable change, but is it good to the nature? Yes, because you saw the emission levels are very low. PM is down, NOx is down, CO is down, HC is down. So you will have a better environment in the coming days. How can we find out the fault in engine by physical testing? I don't know which fault you're talking about, but while testing, you can see there are a lot of, if you have set any limits, I'm just saying if the exhaust temperature should not go beyond 700 degrees. So if we can set an alarm, if anything is going above, we can actually set the safety system and actually not allow the fueling to happen. That's how we can control the faults that are happening. Or because it's an ECU control engine, we can set a limit and also make it not to run beyond any of the set parameters. How a vehicle engine consume their fuel efficiency so that how heavy vehicle engine consume their fuel efficiently so that they get good mileage. I don't know how to answer this, but yes, our target is always the fuel economy. So we make sure that we optimize all our frictional component engine, like we optimize with a better friction component, a high fuel pressure injection system, turbocharging system. There are many things we do. Our target in diesel engine optimization is to meet the emission, but at the best fuel economy. What is the easiest and economical way of engine testing? There are normally mentioned of HC emission, but there is no specific mention of a part. I think this is the question which I answered in the chat box, the same question. But what is the way of emission testing? Economical in the sense, I don't know what is the economy in this. The question is not proper, but I don't know how to answer it. What is the success rate of CFD in designing combustion geometry? How much deviation between predicted and measured emissions are acceptable for industry BS4 emission? Is there any thumb rule as are there to know whether we got the best NOx and soot trade-off for a given combustion hardware system on the test bed in view of many combination EGR flow rate? Does the scope of the incinerator combustion optimization in dimension in the view of BS6 standard where much development will focus on now? I think you are the first question I can answer. Our CFD to the simulation to the final, we are able to achieve within 2 to 4% in the present kind of a situation. But if you can really work harder, I think we can get closer. The target in the coming years would be how to reduce testing. Today, I think we are at 30% simulation, 70% testing. Our target in next 5 years would be how to make it 70% simulation and 30% testing. I've got a last question, but there is something popping up in the front. I'm not able to read. How can we engineers expect future diesel engine to be special, especially with the increasing demand for the fuel? It is increasing prices here every day. Some manufacturers stop production diesel car. Is it something that we must be concerned of? So the diesel car, the concern was the particulate matter NOx actually, but with a lot of advanced technology, with the legislation government has put, we are able to meet those requirements. So in that way, met the emission legislation with the technology, it is possible, but they're going up the board now saying that alternate fuel should be the way out. So we are all working on alternate fuel like CNG, probably hydrogen would be the next, hydrogen IC engine would be the next thing. So it is up to the government to say what should be the limit, and if industry is meeting, they should allow us to produce those vehicles. But if they say, no, you have to have a vehicle which is diesel and flexi fuel. Now, Nitin Gadkari's latest statement is all the way engines we are producing should be flex engines. They say flex means dual fuel. So meeting the emission legislation within the target given, still it is doable with the technology. But if government can be stable with their loss, and this one, it would be easy for the industry because it's a lot of money required to develop this engine, and if we keep on changing the legislation and set standard, it becomes very difficult for us to get back the money that has gone into investment.
I think that's
the only questions there.
Yeah, that one question in the chat box, sir, that is there any equipment is available to measure CH4?
That's what I said. I think I clubbed in another question. The answer to that is It is called an NMHC analyzer, non-methane hydrocarbon analyzer. So the present emission bench separates the hydrocarbon into an NMHC, and we are able to measure it. It's positive.
Okay. I think that's it.
So 1 minute, Robin, 1 second. We participants, we have Professor Ramesh Babu, we have Mr. Yogesh Bolar sir from Ashok Leyland. I think you should all make good use of this session. Are there any questions for the professor? Professor is also here.
Yeah, I am here.
Yes, sir. So are there any questions? You can probably raise your hand and ask questions.
Would the professor like to supplement anything that Mr. Yogesh has told?
Naren, you can unmute and speak.
1 minute.
Yeah, sir. Thanks for the opportunity. This would be a question to Yogesh sir. Regarding the use of diesel engines, I want to know, recently Ford has left our Indian premises and moved on. May I know what would be the major reason to this?
Well, it's a newspaper article. I cannot comment on why they left India, but basically it all depends on the business. So the target volumes, when they don't get, and when the investment is high, it's very difficult to manage the investment and also to reply to the shareholders. So basically, I think Ford had a difficulty to get their product marketed with a high competition coming from Maruti and other people who are already established players. And just not to quote about Ford, it's very difficult in the market, even for a company like Ashok Leyland and Tata Motors, though we don't have much competition. We have 3 big companies, including iShare. The dealer network, the financing, the options that are available, it's not always the technology that is only the parameter. There are many things other than that which actually controls the requirement to sell, to be in the market. So Ford, I think, may not be able to crack the Indian market because of a lot of complexity. Maybe they had, when you cannot increase the volume, what happens, your import content will be very high, then the cost of the vehicle will be more. When you want to compare for the same model, probably the customer might find that 20,000 less, you are able to get a similar feature in a Maruti, people would go there. So it's a lot of other combination which makes a company to sustain in a given market. It is the same if I was supposed to go to an international market and compete with Mercedes-Benz, the challenges I would have, it would be similar what Ford had in India, is what my reply would be.
Okay, sir. And one more thing to add it up, what would you say the future of diesel engines would be, sir?
Basically, yes, diesel, by going by what's happening around, I think the way forward, diesel engines will start tapering, depending on which product it is. For sure, if it is a car, I think it will get replaced by electrical. I think car is electrical vehicles in car would be, two-wheeler be the first to pick up, fast car would be the next. In trucks, it would be the small vehicles in the sub 1 ton or 1 ton to 1.5 ton would be electrical. But larger vehicle, the problem would be the battery weighing capacity would replace the load carrying capacity. Buses would be the first one, because buses, you have a lot more space. So in trucks, I think buses would come. Large size truck of say 35 tons, 40 tons, 50 tons, I think it's a long way to move it into battery or electrical vehicle.
Okay, sir. Thank you, sir. Thank you, sir. To add more, the last question of mine would be as of now, we figured out a way to come with BS6 norms in diesel engines, sir. What if the norms are changing and it goes to extent where diesel engines couldn't find a way, or there couldn't be anything? Will diesel engine be completely substituted at a point, or there will be some share of diesel engines in the moving vehicles, sir?
See, the diesel vehicle will still be available in non-automotive markets where the vehicles are off-road, like for genset, compressors. You really need such kind of engine. But other way we are working is, even myself in the last 3 months, I'm working converting all my diesel engines to CNG. So CNG is somehow acceptable because you don't have a particulate matter, but NOx is there. But we are able to convert with a catalytic converter there. So we are converting our engines into CNG and still will be in the market.
Okay, sir. Thank you, sir. Thank you, sir. That was a great to hear.
Muthu Kumar, you can unmute and speak.
Thank you, sir. So
Yes, go ahead.
Thanks for the nice presentation, sir. I have a doubt, sir. Most of the case emission measurements, their Figas analysis are like that, measuring the carbon monoxide, carbon dioxide, and the hydrocarbon NOx, and like that, sir. And they are particularly measuring the carbon monoxide and carbon dioxide. But in hydrocarbon means they are commonly telling the hydrocarbons. Even the fuel also the hydrocarbons. But they are mentioning most of the case only hydrocarbon is measured. The particulars of that hydrocarbons, like that the previous questions like methane and ethane and some things are anything means presence means how do we measure, sir? But how do we measure one question, sir? Is there any reason behind that, sir? We are avoiding those things. Commonly, we are mentioning unburnt hydrocarbons.
Just to answer your question, if you see whatever the principles on which my emission analyzer, what we are using in the lab, like chemiluminescent detector, NDR, 5-gas analyzers are a very compact one, which doesn't have such a complexity in that they are done with certain other electronic principles. So the accuracy of these equipments is not as level to what we do in the Tesla, which is required as per the legislation. So these are more for the PUC certificates that are offered to the customers just to make sure that the vehicles are not getting out of the limits in the market. So there they are trying to set some limits because you are trying to do only in idling compared to what we do in the loaded engine in the test beds. Okay. So these equipments are not equivalent to what we have in the, in our test beds or the labs. Now, coming to other pollutant, there are many pollutants, but there are various analyzers. So, but for the legislation purpose, for the 5-gas analysis, good enough for the PUC certificates they are doing, and they're feeling that this amount of pollutant, if it's controlled, at least we are at a good level. See, going to a very high level of sophistication requires not many things to be in the field. How do you get it? Who will invest in that? Those are the problems that more than the pollutant part of it. But as you see in BS6 level, we have got something called onboard diagnostics, which I didn't explain because that was not the part of the content. If any of the vehicle gets out of the emission, automatically the vehicle will be not be able to move. That means it has to go to the garage to get it repaired. So there are a lot of clusters in your vehicle which will tell you what has to be done when the emission goes up. So there are many other controls the government are bringing down to control the emission of the vehicles.
Thank you.
Okay, Muthu Kumar?
Yes, sir. Thank you, sir.
Thank you.
Professor Ramesh Babu, you want to add to this, sir?
Yeah, I think it's really interesting presentation by Sri Yogesh with a lot of content and also practical experience. I don't know whether the presentation will be shared with any of them. Sri Yogesh?
For me, it is general, which I can share, sir. It should not be a problem to me. For you, sure, I have already sent, but I can send you the corrected one directly also.
No, the others, students, will they benefit from this?
Yeah, if they're going through it, it's anyway, most of the things which are maybe I will have to little bit tweak to the numbers that I've shown, which is the internal, but I can make the tweak it and change the axis and I can also share it. Should not be a problem.
Probably this may help some of them who would like to pursue their career in the automotive side.
I will do it, sir. No problem.
That's my feeling. I don't know how the PALS is going to handle these things.
If the speakers are okay, we can share the presentations.
Yeah, do you have any drive or something? Because sometimes these presentations are very, very long. Whether you would like to keep them in some Google Drive, the Google Workspace.
This is CNC here. All these PAL sessions are recorded and share the recordings with all the partner institutes. So here they will get to see the slides that Yogesh has put together. If he's kind enough, he can share the PowerPoint with some kind of modification of the numbers. He can actually sanitize the figures in the thing because this may be proprietary.
Yeah.
So that is in the PPT version. So I think the recording will be shared. I think will be all these sessions are recorded because many students and faculty they register due to last minute rush academic work. For example, campus interview or some repeat exam, arrear exam, whatever. May not be able to join. So the recording will be helpful for them to play. As you rightly mentioned, and Sujata already complimented, it's a treasure that Yogesh has shared today. There's so much engineering across various disciplines. So I think it will be useful for the students community as reference material for them.
Yes.
So Yogesh, this recording will be shared with all the partner institutes.
Okay, sir.
There is just one question that is unanswered. I mean, what is the major difference between diesel engine and upcoming e-vehicles? And in the same regard, in the live chat of YouTube also, there is one question saying, will the electric engines replace diesel engine in heavy vehicles in future?
As I said, for heavy vehicles, it's a long way to go, as we need to find the right size of the battery for that kind of a load carrying capacity. So I think it's a long way. Diesel energy to replace by electrical will take some time, but at some point of time it could catch up. But yes, at present, as I said, bus and LCV are the focus that we are looking. For large size diesel engine, the way could be hydrogen or the fuel cell is what we are seeing.
Yeah.
Any other question?
No questions.
That's all the questions so far we have seen.
I think, yes. I request Mr. CMC to propose a vote of thanks.
Arun Dev.
Arun Dev. Yeah, I request Mr. Arun Dev to propose a vote of thanks.
Yeah. So good evening, everyone. Thank you very much for the wonderful session we had today. Let me start. I did, in all seriousness, try to make. Sorry, I did, in all seriousness, try to make a lot of notes about what is going on. But very soon I lost the flow because Mr. Yogesh Bolar's session was so technically oriented and covering a lot of practical aspects as well. I lost the flow there. But anyway, thank you very much, Dr. Ramesh Babu, for setting the context. I liked your comment that design of diesels will evolve, notwithstanding the emergence of electric vehicles. And I think that ties up with the question from some of the students and also Mr. Yogesh Bolar's final comments that at least in heavy vehicles, replacement with battery is a long, long way off. Probably alternatives of hydrogen or fuel cells would be the main thing going forward. Dr. Ramesh Babu also set the context in terms of the main factors in diesel engine design and what are the different aspects and different phases of development of the engine. We then had this wonderful session by Mr. Yogesh Bolar. Thank you very much, Mr. Bolar, for the time and the effort in putting together this presentation. I guess you wanted to share the maximum content in the limited time that we gave you, and therefore had to be a little rapid at that. But nonetheless, it was a very informative and very hard driving presentation in terms of the specifics that go into the development of engines and the compliance of these engines to the latest international standards and Indian standards. I mean, it is indeed creditable that we in India are able to design and manufacture engines which comply with global standards today. And I think a lot of that credit should go to serious people like Ashok Leyland and people like Mr. Yogesh Bolar for the efforts that they put in achieving those conditions. So thank you once again for all your efforts in putting together this wonderful theory to practice session. My thanks to the students and the faculty of our institutes who took the time to understand, to sit in and understand. I did count some 320 attendees in the Zoom call. I don't know how many are there in the YouTube session. I'm sure it was a very informative session. As we said, we would have the video link of this shared with the students so that hopefully some more will take interest and find out something more about what was discussed today. Thank you once again for the PMO and PALS members who put this together. And we hope to have many more sessions like this, technical oriented subjects from Ashok Leyland and from IIT as well. So thank you very much, sir, for the time and effort in putting this together. Thank you, Mr. Ramesh Babu. Thank you, Mr. Yogesh Bolar.
Thank you, sir.
Thank you, Mr. Andevan. Thank you, Mr. Yogesh, for your wonderful presentation. Yeah. Thank you. I think we will keep in touch. Okay.
Yes, sir. Yes, sir. Definitely.
Thank you.
Thank
And,
you.
it was power packed, the time was kept, but the content was
Yes.
also delivered,
Yeah.
so
Yeah.
I was making a lot of notes.
Thank you. Thank you, Mr.
Thank you, sir.
Ram and CNC. No, thank you. Bye bye.
Bye.
Bye bye.
Request the participants to submit their feedback and attend the online quiz. It is pasted in the chat box. Thank you. Thank you, Ram sir. Thank you, Mr. Arun Dev.
Thank you.
Sujata ma'am, thank you.
Thank
you,
you,
Robin.
PMO Sugata, for the Slido, Robin for putting to this.
Thank you.
Thank you.
PVM has joined.
Thank you, Ram.
Thank you.
Robin, you have to stop the live streaming. Pa.
PVM, you can talk now. You can unmute.
No, I was telling you, Robin, that I've been around for some time and listening. I just opened my video now. It was a great session, I think, full of punch, lot of technical